In this video, we're going to talk about how we can get new power series out of the power series that we already have. So one way is we can change the variable. For instance, let's look at e to the 2x. You might remember that the power series for e to the x is the sum from k equals 0 to infinity of 1 over k factorial times x to the k. So what would the power series for e to the 2x? If this is equal to e to the x, well, all we're going to do is connect this x to this x. So the power series for e to the 2x would have the exact same form, but instead of x, I would have 2x raised to the k. So this would be the sum from k equals 0 to infinity 1 over k factorial 2x raised to the k, which I can distribute this k through as a power, and I get the sum from k equals 0 to infinity 2 to the k over k factorial times x to the k. So this would be the power series for e to the 2x, and I get that by plugging in 2x everywhere that I see x in terms of the expression. Look at another example. Let's look at g of x equals 1 over 1 plus x squared and see if we can find the power series representation for this. And the key idea here is that this kind of looks like something we know. We know how to represent 1 over 1 minus x as sum from k equals 0 to infinity of x to the k, and as long as the absolute value of x is strictly less. So 1 over 1 plus x squared kind of looks like 1 over 1 minus x. The only thing that's different is that instead of a minus x, we have a plus x squared. So let's try that. We're going to do 1 minus negative x squared. And then if we take this minus x squared and we replace this minus x, or replace this x with minus x squared everywhere, this will become the sum from k equals 0 to infinity negative x squared raised to the k. And there's, again, a little bit of work we can do here to simplify this. So this will become the sum from k equals 0 to infinity negative 1 times x squared raised to the k, which will be sum from k equals 0 infinity of negative 1 to the k times x to the 2k. Now the question is, when is this valid? Well, because the original expression was valid when the absolute value of x was less than 1, this new expression will be valid when the absolute value of x squared is less than 1, which in this case, it turns out is exactly the same scenario or same situation. Okay, now you try this on your own. I'm going to ask you to find power series representations for e to the x squared and for 1 over 1 minus 4x. Please pause the video, and when you come back, when you're ready to discuss and see what I did. Please try this on your own first. Okay, again, the key for anything involving e to the whatever is to begin with this knowledge that the power series for e to the x is the sum from k equals 0 to infinity 1 over k factorial x to the k. So all I have to do if I'm dealing now with e to the x squared is to replace that x with x squared on both sides. So this would become the sum k equals 0 to infinity 1 over k factorial x squared raised to the k. And now I can make these play together nicely, this 2 and this k. So what this will become at the end of the day is the sum from k equals 0 to infinity 1 over k factorial x to the 2k. So the whole key is to just replace the input variable here with whatever you had before. Now let's look at 1 over 1 minus 4x. So again, I have to start with this 1 over 1 minus x is equal to the sum from k equals 0 to infinity x to the k, and that's valid when the absolute value of x is less than 1. So all I'm doing is replacing this x with this 4x. 1 over 1 minus 4x is equal to the sum from k equals 0 to infinity 4x raised to the kth power. But now this is going to be valid when the absolute value of 4x is less than 1, which would mean that the absolute value of x is less than 1/4. And it'd be more common to distribute this k to both the x and the 4, so that this is rewritten as the sum from k equals 0 to infinity 4 to the k times x to the k.